Good afternoon. Welcome to Krishna's class. We look at some inherent structures of spaces. So, LP as a linear space. We will first look at it as it's a linear space structure that is inherent in it. And then with the tools we have developed to try to make it a normally linear space. And we shall see that it is not very straightforward that you put a norm on that, but the norm itself has to be carefully looked into, and then we have to exactly find out what the norm is. So let us start recalling some of the things that we need or what we have developed earlier and just require the right kind of notations and so on. So X mu is a measure space. With the usual meanings for M is a sigma algebra and mu is a measure. Now we define LP mu. Yes, this is all recalling whatever we have done. F from it's a complex valued measurable function and norm of F P. Now there are three conditions. I mean, of course, F is a complex valued function defined on X, and it's a measurable function, and norm Fp is finite. Now this is true for all P considering all these conditions. So that's the basic notation that we have. Now the first result that we is a linear space over C with usual addition and scalar. So that's the result that we want to. We shall do the proof. Recall the definition of this. Addition is defined as by f of sorry f plus g of this is well defined because these are complex numbers, and f plus g, the function f plus g is defined by f plus x, fx plus gx. F plus g at x is fx plus gx. Now this is true for every x belonging to x, and the scalar multiplication. Alpha belonging to C and X belonging to now this is the definition of addition of two elements of LP mu and scalar multiplication of an element of LP mu with alpha taken from, and this is for, okay. So the first question is so this is the first question. So here we need the tools that we have already developed, because you see that what are the conditions that are required? We have to observe that f is a function defined from x to c. It is a measurable function, and norm f, the p norm of f is fine. Now these are the three conditions that we have to verify. Now f plus g is a function. They are complex value functions. Now, since f and g are measurable, f plus g and alpha f are measurable. This is one of the results that we have proved in the context of developing or looking at measurable functions. So sum of measurable functions, scalar multiple of measurable functions are measurable functions. So what remains to be proved is that this is something that you have to verify, so that the space LP becomes closed under addition and scalar multiplication. Now this is the pre-requirement for LP to be a linear space. Of course, there are other conditions subject to other conditions. Now We shall just verify this. And you know that F belongs to LP and G belongs to LP implies norm of F is finite and norm of is finite for all P lying between 1 and 3. So that is the assumption. Now, by Minkowski inequality, norm of F plus G is less than or equal to norm of F plus norm of G, which is fine. Okay, so that's the straightforward. Norm of this is true for here, and this is certainly which implies further and this is finite. Since norm of P is finite, therefore this is finite, therefore this is okay, which implies alpha F belongs to F for close with respect to addition and scalar multiplication. Now we have to actually verify one after another the other conditions that are required for LP to be a linear space. And we observe that I am not going to give the details of the proof. F plus G plus H is equal to F plus G plus H. Now this follows from the evaluation of this at X is essentially evaluation of this at X. Okay. This is associativity. This is what is called associative. Then you have commutativity with respect to addition. Which implies for every fg belonging to T. So this is the first property that we have, is associative. Second property is, this is commutativity. Then we have to there exists an additive identity. That is 0 of then we see that so 0 acts as an identity. Identity. Now this is it. Now the next point is for every f belonging to minus of fx, and you can easily see that this if f is an element of LP, then minus f is also an element of LP. That's very easy to see. Now this element has the property that is equal to the 0. Therefore, minus f is the inverse element of. Therefore, see, all these elements have, so there exists a identity element, there exists an additive inverse element. Now, further other properties of linear space are verified, namely that lambda plus mu f is equal to belonging to C and f belonging to. Now this is easily so also lambda mu f, and you have 0 into f equal to 0. Now this is the 0 belonging to C, and this is the 0 belonging. So this property is satisfied, and then plus 1 into. Now all these are because you have a what is called the field structure on C. Okay. Now you have imposed or you have discovered a linear space, or you are trying to discover a new structure on LP. Now, when you do that, we have to show that the two or the properties of the field and the addition and scalar multiplication that we have defined on LP, they interact without any conflict, and that is what all these things are doing. For instance, I mean, I am just see, these are all little small things, but as students you should know this. You see that in this part, after this, the first part is how you just keep the scalar along with it and then take the addition of LP. The second part is, see, on LP, on C, you have an addition. So lambda and mu are given, then lambda plus mu is an element of C, And what you are saying is, what is this lambda plus nu of f? This is equal to lambda f plus nu f, and this belongs to L. And this is they are measurable, etc. That's trivial. And then so also, when you take, you have a multiplication among the elements of the field, and if lambda and nu are two elements of the field, you want to know what exactly you mean by lambda nu f. Lambda nu f is lambda of nu f. So once f is there, nu f is in LP, then multiply by lambda, that is in LP, and this is exactly what you call this. Okay, so this is again an LP element, so it's all in LP. So you have the zero element of C, that is the additive identity element of C, and when you multiply this with F, you get zero element of LP. Okay, and then you have the multiplicative identity element 1 of C. So what it does, 1 times F is equal to, okay, or you have minus 1 of F equal to minus F, and so on. So these are all the properties that you can immediately. Over the fields. So now we explore the norm, okay, and look at some of the properties of the norm. The next theorem. Now this is an important research. Then equal to 0. F equal to 0. Almost everywhere. This is important. Now that is the catch that is going to slightly complicate your work or demanding more, insightful analysis to get a normally linear space out of LP. Okay, so we will just explore this. Okay, first we look at this one. We take the case 1 less than or equal to p less than infinity. Okay, so we take zero. What does this mean? This is if and only if mod f to the power p almost every, or f Now this is very important because if you examine this, what is that you have? You have a function integrated over x. Now, you see that on a set of measure 0, it is immaterial what mod f to the power p takes and does not alter the integral. Okay, so no matter what the value takes on on a set of measure 0, you get always this 0. Therefore, all that you can assert is that f is equal to 0 almost everywhere on x. Now, this is a very important. Now, this is going to be crucial in our further analysis. So, the next theorem is okay. I have not it. I have to say what is happening. Norm of taken only this case. So if p equal to infinity, norm of f p equal to essential supremum of what does this mean? This is equal to this over, and if this is equal to 0, so if f is equal to 0, then fx equal to 0 for every x, and naturally this is equal to 0. Therefore, this is equal to 0 if and only if essential supremum of and that happens when look at the definition of essential supremum. Okay, almost every. AE stands for almost every. Okay, so let me just summarize so that this means except possibly on a set of measure 0. That's the meaning of it. Okay. So that gives the almost everywhere terminology. Now the next result is systematic. Semi-normal. Let us first look at what is a semi. on a linear space is a non-negative function defined such that this is a term of say norm of psi equal to 0 equal to 0 psi equal to 0, but that does not mean that norm psi equal to 0 implies psi equal to 0. That I will comment upon. Right? Third property is of course norm psi for when psi belong to y for every this is the general definition of what you call a semi-norm. Okay. Now I want to make a remark at this stage. Right? So this is the what you call a semi-norm. It just falls short of a norm. So we'll make a remark here. Observe that you do not assume See, we have said if psi equal to 0, then because if that is also, if it is true that no. So now what we are assuming is it's a semi-low. Okay. So first of all, let us observe this. So the first thing that we verify is this is because see that the two cases, see that now from the definition, it is clear that this is the infinity. However, norm f t equal to 0 only implies that f equal to 0 almost everywhere. Thus, you may not have you may not have implied. So it falls short of it. That's the problem. The other things are easily verified. What are the other properties? Lambda belonging to C, and so that is done. Now one more property is there. This is of course third property verified. Now we look at the fourth property. This is true for every thus consequently the space LP mu is a semi-normal course. So it's a semi-normal universe. We just fall short of what we are after. So we would have been very happy if we could get this as a normal. Okay. Under restricted conditions, now you can easily see that this becomes a normal linear space. For instance, suppose you restrict yourself not to the LP functions, but only to the continuous functions which are LP, then all these properties are satisfied, and then it will become a normal linear space. Okay. but that would require on X a topology. Okay? We have not said anything about this stage, right? So this is the case that LP mu is with this is a semi-normal space. Now this is of course known as the triangular inequality. This is what is called a homogeneity. And this is what's called inequality. Obviously coming out from geometry. I'll just discuss this later, why it is called so. And you are aware from your usual linear algebra, all these facts. Now, using a semi-norm, we can define what is called a pseudometry. What is a pseudometric? Suppose Y is a function defined from we'll just give a notation for that. Name for it. D is called a first thing property is that D of greater than or equal to 0. This is what is called the distance between the points psi and eta. Then that's the first property. Second property is D of psi eta is equal to, it simply says that the distance from psi to eta is the same as the distance from eta to psi, which is something that we are all familiar with in the in our usual parlance of a distance from a city A to a city is the same as the city A. I mean, as you have wild restrictions like you have to travel around different paths. Okay. And of course, eta psi is also belonging to y cross. Or I'll put it psi eta. Then the third property is that is the triangular inequality again. Zeta psi. Then D is called a pseudo matrix. Or y d is pseudo matrix. That's the definition. Now this is a metric. So we'll make a remark. A pseudo metric if d of so here just not we have not said anything about it. We have said that d psi eta is greater than or equal to 0. Whenever this is equal to 0, see, one thing is clear. If psi equal to eta, okay, we have not said anything. And of course, and see, see, if psi equal to eta, equal to 0, but we require d psi eta to imply that is if and only if. So if this is the one that is satisfied in place of this one, the first one, then you have then This in turn implies that it's a topological space. So you are giving a topological structure to LP. I mean, in our situation. So what we do now is that proof. Fine. DP oh, see that for Fp of G belonging to LP, F minus G is an element of LP. So on that we are now defining a function from what is called LP cross LP denoted by dP such that this is true. Then 0 2 whenever F is G. Okay. Now the third property is okay. What does this mean? This comes from the fact that, of course, this is norm F minus G. This is the reason. So here, F minus G equal to 0 almost everywhere, and that means F is equal to G almost everywhere. Thus, we cannot infer all that we can infer is that it is almost everywhere 0. So this is the problem. So we look at the third property. Now these are all trivial to verify. PP symmetry. This is a consequence of the definition. Follows from the definition. So that follows from the definition. And the final property that you have to verify to make it a pseudo norm is that now that's quite easy. This is because norm of which is equal to this is less than or equal to norm of follows from the properties of the semi-norm. What you call triangular line. Finds a pseudo-metric on LPV. So that's what you have. So dP is falling short of becoming a metric. Therefore, it defines only a pseudo. So LP mu dP is a pseudo metric space.